Today you're going to learn about the wheel and axle along with its mechanical advantage. The invention of the wheel was probably the most important invention by humankind, but when people put an axle through the center, it made that invention even more valuable. So one of the greatest innovations of all time. A wheel is actually just a very simple lever, and it's attached to a shaft, which we call the axle. A wheel and axle is to help you move or lift an object by rolling. It is really, really important to be able to differentiate between the effort and the resistance. It could be the wheel or the axle, depending on application. So you have to take a look and say, okay, here's a steering wheel. The steering wheel is connected to a long green axle that goes into the engine space past those pedals. So what am I turning? Right? What am I turning? I'm turning the steering wheel. So that's where the effort goes. The resistance goes into that green shaft, the axle. So in this case, the steering wheel is the effort and the axle is the resistance. But in the case of our car axle with the two tires connected to either side, the torque comes from the engine and it spins in this fun looking gear, and so the axle is turning. That's where we're putting in the effort, and the resistance in this case is the tires on our car. Right? So the axle is turning effort, and as a result, the wheels on the car are turning resistance. So depending on application, you want to think about it. Where is the work? Where is the energy being put in? What is it that you are turning versus where is the work being done, or what is being turned as a result? So we've already talked about the 4 measurements for simple machines, and we're going to talk about them again in terms of a wheel and axle. So for a wheel and axle, the effort distance is the distance traveled in 1 revolution. It doesn't matter if it's the wheel or the axle. They're traveling in a circular pattern. So 1 revolution is 1 time around. What's 1 time around a circle? Right? That's the circumference. So 1 time around, you're calculating the circumference. So DE is 2 pi r. Right? 2 pi r. We talked about that already. It could be for the wheel or the axle. Just think, where is the effort being applied? The resistance distance is also the distance traveled in 1 revolution. And to save space and notes for you guys, I only wrote down the formula. dr also equals 2 pi r, the circumference, and then just refer to the rest above. It could be the wheel, it could be the axle, but either way, it's just the distance traveled in 1 revolution. The forces also mean the same thing, and we just want to look at where those forces exist in a wheel and axle. Here we have a toddler turning a doorknob, always exciting yet dangerous. The effort force is the force applied to the wheel or the axle to turn it. So in this case, the knob itself is where the hand is applying the force. So that's your effort force. It's what the hand is doing. The axle is the part of the doorknob that actually goes into the door. And that's what's going to turn as a result. And so that's where our resistance force is applied. So effort force, basically where the hand is, right? Where is the force being applied to turn something? And resistance force is what is turned as a result. We talked about mechanical advantage. Mechanical advantage is the advantage you gain by using a machine. So in this case, how do we calculate the mechanical advantage gained by using a wheel and axle? The formulas are the same. Okay, the ideas that we learned with levers, same. Ideal mechanical advantage is the effort distance divided by the resistance distance. The ideal mechanical advantage does not consider friction, right? It's ideal. It's in a perfect world. If we take the formulas we talked about a couple slides ago, knowing that the effort distance is a circumference and the resistance distance is also a circumference, we can fill in this formula. So 2 pi r, and I put resistance radius on the bottom and effort radius on the top. Well, what happens? We talked about this last week. Anything on this top and the bottom that are identical cancel. So your 2 pi on top cancels your 2 pi on the bottom. So we don't need 2 pi at all, which makes calculator way nicer. So really, the ideal mechanical advantage is just a ratio of the radii or the diameters. It really depends on what information you're given and how you want to work the problem. So IMA is the effort radius divided by the resistance radius, or the effort diameter divided by the resistance diameter. So that's going to be important. We're going to definitely circle those formulas. And I put a little reminder. Lowercase r means radius. Lowercase d means diameter. Actual mechanical advantage is the same formula we learned before for levers. It is the resistance force divided by the effort force. Nothing different there. The efficiency of the wheel and axle is still the actual mechanical advantage, which does account for friction, divided by the ideal mechanical advantage, no friction, times 100. Don't forget that part because you got to make it a percent. So those are our 3 very important sets of formulas that we're going to use to calculate mechanical advantage and efficiency for wheel and axle. Now, we're going to see some different examples this time. So when we did the lever, we calculated IMA, we calculated AMA, we calculated efficiency. This time for wheel and axle, we're going to add a different kind of problem where we know one of the mechanical advantages because we can easily calculate it, and we know the efficiency. And then we're going to work backwards to find the other mechanical advantage and a missing force or a missing dimension. So we're going to switch up our example types here just a little bit. So here's a typical example of a wheel and axle problem. A wheel and axle assembly has a wheel of 60 centimeters in diameter and an axle of 7.5 centimeters diameter. Letter A, neglecting friction, calculate the mechanical advantage. So we know both diameters. Go back to our previous example, our previous slide with all the equations on it. IMA equals effort diameter over resistance diameter. Pardon my sloppy writing. So take a look at the diagram. You can see that the effort is being placed on the big wheel of 60 centimeters. The effort is being pulled down. The resistance force, that 220 pounds, is pulling on the axle. So this is kind of like a well, right? You crank the wheel and you lift a weight. So our effort diameter is going to be the 60, and our resistance diameter is going to be the 7.5. My centimeters cancel, right? Because I'm dividing. And I'm going to use my calculator. And I'm going to type in 60 divided by 7.5 equals 8. So IMA equals 8. That's part A. Part B says, find the effort in newtons or pounds required to raise a mass of 100 kilograms or 220 pounds. So in this case, we're going to assume that the efficiency is 100%. And I can do that for two reasons. One, they don't tell me a different number of efficiency. And two, in part A, we neglected friction. So I'm just going to say, okay, we're going to neglect friction in part B too. So now I'm going to use my AMA equals FR over FE. But because we're neglecting friction and we're assuming 100% efficiency, our AMA actually equals our IMA. So I could say 8 equals the resistance force of 220 pounds divided by our effort force, which I don't know. Okay, now here's where things can get tricky. You have to remember your algebra, okay? And don't be scared. Algebra is just the manipulation of numbers, right? So just remember your math steps. You cannot solve for a variable like FE in the denominator of a ratio. Okay, I'm not even going to use that F word, fraction. So you cannot solve for a variable in the bottom of a ratio. It has to get moved out of there. Currently, we're saying it's 220 divided by FE equals 8. So you have to undo the dividing. So you can actually multiply both sides by FE. On the right, those cancel. And now you have the effort force times 8 equals 220. Well, now that looks much nicer, right? Because to get FE by itself, you just have to divide both sides by 8. So FE equals 220 divided by 8. I'll put my pounds in here in a second. So I go to my calculator, 220 divide 8 equals 27.5. Man, that's sloppy. Sorry, I don't have my pen, which I usually use to write on my screen. So we found the mechanical advantage neglecting friction, the IMA. We used that and the assumption that a wheel and axle in this particular example is 100% efficient. And we found the effort force is 27.5 pounds. So with the small effort of 27.5 pounds, that's about how much my dog weighed when she was a puppy. I could basically put a harness around her, attach it to the rope on the wheel, and let her fall to due to gravity slowly, and it would lift a 220-pound object. So that's pretty amazing. A little puppy could lift a 220-pound person, right? That's a person who's about 6'4" and in athletic condition. So that's some good mechanical advantage. All right, let's take a look at our last example. Here we have a bucket attached to an axle with a wheel, and it says, what is the IMA? So we have the axle as diameter of 8 inches. The wheel has a diameter of 20 inches. So I'm going to take my IMA is the effort diameter divided by the resistance diameter. That is, let's think about this. The bucket is being lifted, right, by the axle. The axle is being turned by that handle. So the big wheel is the effort, and the axle in this case is the resistance. So I'm going to do 20 divided by 8 equals, again, sorry for my sloppiness, 20 divided 8 is 2.5. So my ideal mechanical advantage is 2.5. Now it says, what effort force should be applied to lift the bucket? The bucket weighs 25 pounds. The bucket weighs 25 pounds. Let's see. I'm going to skip down here to letter C real fast. What's the efficiency? We don't know the effort force. We don't know the effort force. So we can't calculate AMA like we did for levers. So we're going to have to think about, okay, well, I don't have information on the actual mechanical advantage. So I'm going to have to assume that this wheel and axle is frictionless. It's the only way to find the answer for the effort force. So for C, I can't actually calculate that. We have to assume 100%. That's a percent sign. Because we don't have enough information. And we got to calculate the effort force. So I'm going to do the same thing here that I did on the last slide. And I'm going to say the AMA actually equals the IMA because of no friction. And that is the resistance force divided by the effort force. So 2.5 equals the resistance force, 25 pounds, divided by FE. So you're going to have to do the same thing. Okay, now shortcut. All you have to do when you have the variable in the denominator is take the top number. I'm going to draw a little arrow here. Take the top number divided by the number on the other side of the, put that decimal in there, of the equal sign. Okay, if you go back to the previous example, that's what we did. So we're just going to take the top number divided by the number on the other side of the equal sign, and that will give us FE without showing our extra step. So 25 divided by 2.5 is 10. So our effort force is 10 pounds. Oops. Get that thing off of there. There we go. 10 pounds for our effort force. So that's letter B. These two examples are very similar to the problems you're going to do in today's activity. The distance learning activity for wheel and axle. The link is in the announcement. It's also on your content page. If you drill down in Unit 1 to there are simple machines, it has it on the information page for the unit that we're in, 1.1. So use these two as examples to help guide you through that activity. And we're going to talk about that when I get in on Wednesday. So make sure it's done so that we could check our answers and talk about anything that we might not understand. Excellent. Good luck.